follow. In the last class, we have discussed about the different operations on sets, like union of sets, intersection of sets, difference of sets, complement of sets, etc. Today we will go further now. We will study today about the algebraic property of set operations. Algebraic property of set operations. Or laws of set properties or laws, any you can say laws of set operations. So okay. First I will give you the laws and then you require the proof of some important one also. The first one is called idempotent law. Idempotent law. It is A union U equal to U, A intersection U equal to A union A equal to A intersection A equal to A. With a different example, we have already done the proof exactly, but we will do logical proof. This is number one. This is number two is commutative property. Just like arithmetic, you have done commutative property, associative property, distributive property. Same thing here, but in different way. So A union B equal to B union A. This is our intersection also. A intersection B equal to B intersection A. See 2 plus 3 equal to 3 plus 2, like that 2 into 2. Then number 3, identity. Law, better right. Here in arithmetic also you have done identity. 0 is the identity element. Similarly here. You understood what we like? A union phi equal to A intersection phi equal to phi. Then you have associative property. Just like that, 2 plus 3 plus 4, like that. Similarly here, our union also, our intersection also. A union B union C equal to A union B union C, just like arithmetic. A intersection B intersection C equal to A intersection B intersection C. Understood? Then De Morgan's law. It's the name of the mathematician. He discovered the law, which is known as 2 here. A union B whole complement. You remove the bracket, then it will become intersection. And conversely also, A intersection B whole complement. When you remove the bracket, it become intersection will become union. Then of course you have distributive law property. Distributive property or distributive law, anything you can say. This is, see, just like that. A into B plus C. So A union B intersection C. A union B intersection A union C. Other one also, it can be that 3 into 5 minus 2. A intersection B union C, the intersection B union A intersection C. Then very important is difference law. Difference law very important. A minus B equal to A intersection B complement. This is called difference law. Complement law also I already we have done complement law. So let me write it once again. Complement law. We have the idea. You know A complement, whole complement, how do we get A? U complement, we will get 5 in your previous class. We have discussed about the definition of complement and this property also I have given you. 5 complement equal to what you will get? U. See, A union A complement you will get U and A intersection A complement you will get 5 because what is A? That is not in A complement. So these are the property of set operations. These are the property you should know, and proof also needed, but some important one I will give you the proof. Okay? So now we will discuss with the proof of some important ones or difficult ones. Easier you can do yourself. Let us prove distributive property. A union B intersection C equal to A union B intersection A union C. Distributive property we will try to prove. See, equality of sets, we have the idea. Two sets A and B are said to be equal if A is a subset of B and B is a subset of A. See, we have the elements suppose 1, 2, 3. We have the element 3, 2, 1. Every element of A are real and every element of B are real. Here A is a subset of B, B is a subset of B. In that case, if A will be equal to B. So to prove A equal to B or this equal to this, we need to prove this is a subset of this and this is a subset of this. So start now. Let X belongs to A union B intersection C. What is the meaning? You know what is the meaning of union? We have discussed already. That means X belongs to A or X belongs to B union C. This is the meaning of union of sets, U. Now, so X belongs to A or can remove the bracket. Again, meaning of union, intersection, What is the meaning of intersection? X belongs to B and X belongs to C. Now remove the bracket. X belongs to A or X belongs to B. This and this together and X belongs to A or X belongs to C. Here. X belongs to B. A or X belongs to B. Then and X belongs to A or X belongs to C. Now, what is the meaning? X belongs to A or X belongs to B. What is the meaning of our union? The X belongs to A union B. Okay. Then what is the meaning here? And what is the meaning of this? X belongs to A union C. Now, see X belongs to A union B and X belongs to A union C. What is the meaning of AND? We would AND when they confirm in this set also and this is a confirmation. X belongs to A union B and means confirm means it is common to both, so intersection A union C. Now here we have started from X belongs to A union B intersection C and we have arrived here X belongs to A union B intersection A union C. What is that? What is the meaning? It means that what elements are here, same thing are here, so everything of these are here also, so this is subset of this. What will get? A union B is a subset of A union B intersection A union C. Now what I explained you to prove A equal to B, you need to prove A is a subset of B and B is a subset of A. So to prove this equal to this, we need to prove this is a subset of this, and conversely this is a subset of this also. It becomes a long process, there are various shortcut methods. If you give this both way implication sign, or if you know leave sign, and then no need to do it again. You can write directly that this is a set of this and A union B intersection A union C is a subset of A union B intersection C. See, suppose this is a 1, this is 2, from 1 and 2, this is a subset of this, and this is a subset of this. What do we get? A union B intersection C is a subset of A union B, sorry, not equal, A union B intersection A union C. This is shortcut method. We will use this method only. We can do again long also method same only. But when you get both way implication, then we have already done in both way. If you are able to prove this is a subset of this, so this will also a subset of using this time and shortcut. So this is the first hence proof. This is a very important property, this symmetry property to prove. Similarly, we can do another one. Okay, one more important one I want to explain you. De Morgan's law. There are two, both are similar way also, but if you understood to write down De Morgan's law. Okay, there A union B whole complement equal to A complement intersection B complement. This is De Morgan's law, first one, over union. We have another one also over intersection. Almost similar only if you understood this one. Try to understand this. So start now. Let X belongs to A union B whole complement. You know the meaning is what? X belongs, if X is in A. Here, suppose U equal to 1, 2, 3, A universal set, I is a proper subset of U with the element 1, 2. And you know what is A complement? What element of U are not in A? That is 3. Now see here, if 3 is in A complement, 3 never will be in A. So same way, we will understand if X belongs to this complement, X does not belong to A union B. Understood? If 3 belongs to A complement and 3 does not belong to A. So same thing here. X belongs to this complement, X does not belong to this. Now here is a twist here. X does not belong to A. Union means all. But that is in case of belongs to. If it does not belong to, it will become A. You know why? Try to be clear. What it means? Union means all. All means either in A or in B. If any element are there, any element there in A, it may be in B, may not be in B. If it is in A, it must be A union B. If X is not in A union B, so it confirms that X is neither in A nor in B. Confirmation, and confirmation is right. Clear? So if X does not belong to A, if 3 does, if 1, 2 does not belong to, 3 does not belong to A. Here, 3 does not belong to A, then where is 3 A complement? So X does not belong to A, then X belongs to where? A complement. And X does not belong to B means X belongs to B complement. Understood this? If 3 does not belong to A, then where is 3? A complement. Okay? And belongs to confirmation and intersection. X is in A complement also, and it confirms that X is B complement also. That belongs to A complement intersection B complement. So therefore therefore, see, we have started from here and arrived here. What is the meaning? Every element of here belongs to this or also belongs to this. Okay? So therefore, what we will get? A union B whole complement is a subset of A complement intersection B complement. But if you give both way application, then you can write this is a subset of this also. A complement intersection B complement subset of A union B whole complement from 1 into what we will get? Whole complement equal to A complement intersection B complement, hence proof. That's why you can